more or less. More important thing is the intuition, yeah? So general understanding of how it works. If you don't get the mathematics of the differential equations and all of these derivatives and so on, that's fine, but the idea, do you get it? Because it's important for you in order to train neural networks.
So basically, if you understand the last lecture had the math part isn't not if the last is intuition.
Yeah, it's more important the intuition rather than the mathematics itself. Yeah, the mathematics you will see a lot later on. Okay. Good. So
okay.
now we're gonna talk about some practical aspects of training neural networks. So really, how do I train a neural network in practice? So we're gonna first talk about activation functions. We talked about one activation function, the theta, which is tan h. We're gonna look at other methods or other activation functions and trade off these activation functions, which ones are better. Then we're going to talk about regularization. How do I regularization in neural networks? There are various techniques for doing regularization. Then data pre-processing and weight initialization, very important aspects in neural networks. We'll talk about optimization algorithms. So yes, they all use gradient descent or backpropagation, but there are techniques to make this better or optimize the training of neural networks. And then we'll finally talk about hyperparameter. Okay. So again, the neural network is nothing but some weights and some neurons, right? So activation functions, theta, which happen to be nonlinear. So the first question is, why do you need a nonlinear function? Why is theta nonlinear? Okay. So the answer to this is that why not a linear function? Why not just use a linear function? So basically the neuron outputs the signal as is without raising it to the power of e and then using tan h or sigmoid or something like this. Why not just pass the signal as is? Still have layers and multiple neurons, but then just pass the signal as is. So that's what I mean by a linear function. And the answer to this is equivalent to a single neuron or perceptron. So let's see what do I mean by this. So I'm gonna try to draw this. Okay. So assume I have just a single neuron in multiple layers. So I have the input here, single input, x. And then it goes through a neuron, goes through another neuron, another neuron, and then the output. So that's h of x. Okay. So let's say this is W1. That's W2. That's W3. And then the output, right? And the activation is linear. So whatever the signal is, I output it as is. I'm claiming that this is equivalent to a network which looks like this, a single neuron with x here and some w, and I have my hypothesis h of x. So why is this the case? Why is h of x in the above one? If this is a linear function, it's nothing but
x times w1, then the answer we multiplied by w2, then the answer كمان لنوصل لعند ال h. We can do the same using
yeah, which is basically w1 times w2 times w3 times x, right? In the above network, this is what is correct. So I can call this w, of x. So basically, the network doesn't need to learn 3 different weights. I can just learn 1 weight multiplied by x, and that would be equivalent to the network above it. Yeah, you can assume, you can generalize this to multiple neurons per layer and doing summation and so on. Eventually, if I'm not using any nonlinearity, I'm getting to a single neuron, a network of single.
So it's useless?
Now?
So it's useless to do a linear.
Yeah. You never use in a neural network. You always have to use nonlinear functions as activations. Okay.
Okay.
So when you're doing a library, when you're training a library, let's say Keras or TensorFlow or something like this, or even sklearn, and you build a neural network, one of the things you have to specify is the activation function of the neurons. Yeah, and if you use a linear, then it's useless. You know that it's basically as if you're not doing any neural network. You're doing just a single perceptron. So we really need to use non-linearity. We looked at one non-linearity, which is tan H in the previous set of slides. We're going to look at other ones in a bit. Stop share. Okay. So 3 popular choices. I have the sigmoid function, the tan H function, and the rectified linear unit. This is the sigmoid, this is the tan H, and this is the value. Sigmoid, we've seen before, where?
Logistic regression.
And logistic regression, excellent. Yeah, so logistic regression, use the sigmoid function. It squashes the signal between 0 and 1. So it's a probability, right? Takes a signal and turns it into a 0 and 1. Okay. The tan H, the one we played with in the previous set of slides, so it squashes the signal between -1 and +1. And the ReLU looks like this. It's a maximum of 0 and S. So it takes the signal. If it's negative, sets it to 0. And if it's positive, outputs the signal. So it's similar to a linear in the positive range, and in the negative range, it's 0. So it's non-linear, yeah? It's still non-linear. It's not a linear method, but it's all positive. In the positive range, it's linear, and in the negative range, it's 0. All right? So let's see the sigmoid activation function. Can I use it, or is it recommended to use it? So the properties of it. It squashes the signal to the range between 0 and 1. So if the signal is very negative, it becomes 0. If the signal is very positive, it becomes 1. And in the range, in this range, it's almost linear. Yeah, and the formula for the sigmoid function is this: 1/1 plus e to the power of minus s. Okay, it's historically popular since they have a nice interpretation as saturating or firing of a neuron. So in the brain, right, neurons get fired or saturated. So we pass a signal, right, to the neuron, and then the neuron gives me, you know, +1, either doesn't output anything or it outputs something, right? So that's why it has some biological similarity to the brain. Okay, now it has 3 problems. These are very important problems. So these get you get asked a lot about this in interviews, and job interviews, and master and graduate studies interviews. So these are the things that show that you understand neural networks more than, you know, the mathematics. So saturated neurons kill the gradients. Okay, we'll understand this. So just to look at it, to understand it clearly, look at this. What is the gradient or the slope when the signal is very positive?
0? Mostly 0.
It's 0, right? And what is the gradient when the signal is very negative? It's also 0.
0.
Yeah, so basically, these when the signal is very positive or the signal is very negative, you get that the gradient is 0. So why is this a problem? Remember that I'm backpropagating the gradient from a previous layer, from one layer to the previous layer. Okay, through this formula. Okay, so I would have this theta dash of SI of L minus 1. If I'm using sigmoid at the theta, I will get this theta dash of SI of L minus 1 to be 0 if the signal is very positive or very negative. Yeah, which could happen a lot. So I get basically that the deltas become 0 because this is 0, right? When the signal is very positive or very negative. So this kills, right, the gradient from the previous layer. And I end up with delta I of L minus 1 equal to 0. I use these deltas to update the weights. So if these deltas happen to be 0 because the signal is very positive or very negative. So if the signal is very positive or very negative, these deltas becomes 0. And so this whole component becomes 0. And what do I get? I get the new weight is equal to?
The same weight.
The same weight. So basically the weights do not get updated. So when I use sigmoid, what happens is in a lot of the cases, the weights just after a few iterations or few examples or few outputs, the weights do not change anymore. So basically they stay the same. Even though the error is high, the weights do not get updated. So that's the issue with zero gradient problem. If I use sigmoid, it tends to, the weights tend to not get updated when I'm training the neural network. Okay? Because of the zero gradient problem. Okay. So that's the first issue with sigmoid. Second issue is that the outputs are not zero centered. What do I mean by this? Look at it, right? The output is between 0 and 1. So it's not centered around the 0. The output of, or the activation of a neuron is not centered around 0. It's a value between 0 and 1. Okay, so it's centered around 0.5. Why is this a problem? Let's see. So actually, output of a sigmoid function is always positive in the range of 0 and 1. We know that, right? That's the definition of the sigmoid function. So what happens? I have the gradient, the partial derivative of the error with respect to the weight is equal to partial derivative of the error with respect to the signal times the partial derivative of the signal with respect to the weight using the chain rule, which is this times xi of L minus 1. We've derived this in the previous set of slides. Okay. I know that xi of L minus 1 is positive, is always positive. So it's between 0 and 1. So it's a probability. So it's between 0 and 1. So it's always positive. This means the following. This means that this partial derivative, the delta, or this guy is the only thing that decides on basically the sign of the delta or the sign of the update for the weight. Yeah, so I update the weight based on this. Yeah, I multiply this by eta and then subtract from the old weight to get to the new weight. So now this is always positive, so it doesn't play any role, it only adds. And this is gonna be either negative or positive. And so all the weights in this, on these edges, all the different edges here, right, that are contributing to the signal will be either increased or decreased, depending on the sign of this. So if the sign of this is positive, then you'll have to increase the weights on all of these guys. So we do W of the old weight minus, right, the value of this, which happens to be all positive. Or you add or subtract, basically. So you always add to all of these guys or subtract from all of these guys, right, from the old weights.
Sir, can you repeat the last thing you said about updating the weights?
Mm-hmm. So this, you know that this is between 0 and 1. You agree? This is positive.
Yes, the sigmoid function.
Okay. Now I have this, the other component. The other component will have a sign, either positive or negative. This delta or partial derivative of the error with respect to the signal here. This is going to be either positive or negative, correct?
Yes.
Okay. Now, what happens to the weights on all of these edges that are feeding into this neuron? All of them will either be increased by some amount or decreased by some amount, depending on the sign of this. So all of these edges, I either increase them, the weights, I increase the weights from the old weights, or decrease them. You see it? Because this is how I update the weight. So I update the weight by saying the old weight minus this times the learning rate eta. So if this is positive, then I'm subtracting from the old weight for all of these edges, for all of these weights. And if this was negative, then I would be adding to the old weight. So the old weight for all of these edges, times, right, the value of this times the value of this. So I either increase all the weights or decrease all the weights. You see this now or no?
Yes, sir. Thank you.
You're welcome. Okay. So why is this an issue? Let's say I have two weights only in the network. So W1, which is the x-axis, and W2, which is the y-axis. Okay. Remember that, right? I can only either increase both weights or decrease both weights. So these are the green areas are the allowed gradient update directions. So I can increase W1 and W2. So here is in this green area, I can increase both of them. And I can decrease, or I can decrease both of them. So I can do increase one and decrease one. This is not possible, yeah, because of the non-centrality around the of the sigmoid function. Okay, but let's assume that the optimal weight is here. So that's the weight that minimizes the error. So what happens here, right? Ideally, I need to do what with respect to the weights? Can you tell me what should I do with respect to W1 and W2? So if I have a current values for W1 and W2, which were here, starting here at this point, what should I do to the weights, W1 and W2, to reach this ideal weight?
I either keep increasing or keep decreasing. But I take one way. I can do both. Right?
Yeah, but ideally, if I didn't have any restrictions, what would I have done? If I didn't have any restrictions, what do I need to do to reach this weight, given the current weight? What do I need to increase? Which weight do I need to increase? W1, right? I want to increase W1. To reach this weight, I want to increase from here. I want to increase W1 and decrease W2, right? So W2 should decrease. So it becomes right in this area, in this direction. So I should decrease W2 and increase W1. But I'm not allowed to do this. I either increase both of them or decrease both of them. So what do I need to do? I will have to do a zigzag path. So I decrease both of them a little bit. So I decrease W1 and W2 a little bit. That reach me here. But then I realize, oh, this weight is not so good. I need to increase both of them. So I increase both of them a little bit. And then I decrease both of them a little bit. And then I increase both of them a little bit. Decrease until I reach the optimal weight. So I have to do this zigzagging, right? Until I reach the optimal weight. And instead of really going for the forward direction and keep on decreasing W2 and increasing W1 to reach the optimal weight. So what does this entail in terms of training? Any thoughts?
What's the question?
What does this entail in terms of training? So what happens in terms
It takes more time to converge?
It takes more time to converge, right? Training becomes very slow. Yeah? So when I have this non-centrality around the zero, it limits my ability to update the weights. So I don't have the freedom of updating the weights in any direction I want, and that makes the training very slow. Yeah? So that's the second issue with Sigma. All right? Okay. Finally, exponential is a bit expensive to compute. Why? Because I have to, the sigmoid is a bit expensive to compute. Why? Because I have to raise the signal to the power of E, right? Multiply by -1 and raise it to the power of E. So this is a little bit, exponentiation is a little bit expensive.
Seriously, is it a problem?
It's a problem when you have a huge network. Yeah, so you have a huge network with, it's common to have networks with millions of neurons or millions of weights and stuff like this. This becomes expensive. You have to multiply the weight by the feature values, raise this to the power of e, and pass it to the next layer, and so on. And you might have a lot of layers and a lot of neurons, 200 neurons, for instance, and 10 layers or 20 layers or 100 layers, and that becomes expensive overall. Yeah.
Yes.
So then we don't use sigmoid function.
We're not going to use it except for the output layer. I'll tell you at the end the summary of this, where do we use the sigmoid function. Yeah, so we usually use it for the output layer only for doing binary classification. All right?
Okay.
All right, so let's see the tanh activation function, which is the one we used for the derivation of neural networks when we talked about it in the previous set of slides. So what does it do? It squashes the signal between -1 and +1. So that's the formula for tanh, and it happens, it takes the signal, if it's very positive or it's very positive, it becomes +1, very negative, it becomes -1, and in between it's linear, almost linear.
It is centered by 0, so we got away from one problem. But however, we have 4 exponentials here. Like it's
yeah. So it's it's 0 centered, obviously. So it's centered around the 0. So it's between -1 and +1, meaning what? Meaning that I can update some weights by increasing them and some weights by decreasing them. So I got over the issue of this zigzag thing. So that's a nice thing. It still kills the gradient when saturated. Why? Because the derivative here is 0, the derivative here is 0. So it has the same issue with the 0 gradient, right? Basically the weights might not get updated. And it's still expensive because I have this exponentiation 4 times. Yeah?
Yes.
Okay. So now it's also not ideal. Now, okay. Yes, Ziad. Then get why the weight wouldn't get updated. Okay, let's go back to this. If this is 0, right, theta dash of Si of L minus 1, which happens to be the derivative of the signal with respect to the signal, the derivative of the activation function with respect to the signal, if this is 0, all of this becomes 0. Okay, so this guy becomes 0, and so the gradient becomes 0 as well. And I'm using this gradient to update the weights. The weight is equal to the old weight minus eta, which is the learning rate, times the activation, times delta J of L. If this delta J of L is equal to 0, all this component gets to 0, and so the weight becomes the old weight. So this happens, right, because of the gradient becoming 0. If the gradient becomes 0, then this component dies, and I get the old weights to be the same as the new weights. Does this clarify? Okay, good. So this happens as well with the tanh. If you look at the tanh, right, when the signal is very positive or very negative, so very positive here, very negative, if you take the slope of this, which is the gradient, that's 0. So basically this happens a lot, or could happen. Yeah, if the signal is very high or is very low, you end up being screwed. The weights do not get updated, so you're not learning anymore. Okay, now the radio function is very cool. It doesn't saturate, at least in the positive region. If you look at the positive region, if I take the derivative, it's basically +1. The gradient is +1 in the positive region, so it never gets saturated, right? It's never 0. So I don't get the issue with the weights not being updated. It's very computationally efficient. It's basically maximum of 0 and S. What is the signal, right? If it's positive, output it as is, you're not raising to any power. And if it's negative, output 0. So it's very computationally efficient. It converges much faster than sigmoid tanh in practice. So if you use ReLU or rectified linear unit as your activation functions in the neuron, it usually converges much faster. The training is much faster in practice.
Isn't this linear?
Is it what?
Linear?
It's linear in the positive region only, And in the negative region, it's 0. So it's not linear.
But so aren't we also killing the gradient here for the negative values?
Yeah, but we'll see why this is works, right? So gradient is 0 in the negative region, as you're saying, and this doesn't happen often in practice and used as a form of regularization. So what does this mean? It means that for certain iterations, yeah, when the signal is negative, you don't update the weights, and that's as you're doing this as if it's a form of regularization. Yeah, you're saying, okay, I'm not going to update all the weights of the network, so this is not going to happen for all the neurons or for all the weights. Yeah, some of the signals will be positive, some of the signals will be negative, and so in every iteration, you're kind of updating some weights and not updating all the other weights. All the weights that whose signals are negative are not going to get updated, or all the the neurons for whose the signal is negative, their weights are not going to be updated, and that's fine because you're doing some sort of regularization. You're not updating all the weights all the time.
Sir, can't we مثلا for the negative values take their relative symmetric value with respect to the x-axis ونعملها as if it was positive?
So there is another form of ReLU. I'll show it to you in the next slide, but let me finish this first, and then I'll show you a different form of ReLU, right? A more general form of ReLU, yeah? That overcomes this issue of the gradient being 0 in the negative region, okay?
Okay.
So it's more biologically plausible than sigmoid as well, because, right, it outputs something between like 0 and positive, yeah? So it works similar to the brain more than sigmoid. Okay. So sigmoid is really a probability between 0 and 1, and that's not how the brain works. Yeah. Okay. It's not zero-centered, of course, as you see, and the gradient is 0 in the negative region, but this is a form of regularization. To be very precise, the gradient is undefined at the 0. Yeah, so in this area, it's similar to an absolute function. Yeah, where the gradient is not the derivative is not defined at the 0, but you can assume it to be either 0 or +1. Okay, good. Now, finally, and we'll stop here. The leaky ReLU, right? So the leaky ReLU is a generalization of the ReLU activation function, and it's maximum of 0.01 S and S. So in the positive region, it outputs the signal, and in the negative region, it outputs 0.01 times S. Yeah, so it's the derivative here is not 0 anymore, so you don't get the 0 gradient problem, or it doesn't saturate. It's very computationally efficient. You just multiply by 0.01 or output the signal as is. And then again, converge much faster than sigmoid and tanh in practice. It will not die. So basically, right, there is no 0 gradient problem. And there is a more general form, which is you do maximum of alpha S and S. Yeah, so alpha being a parameter, a hyperparameter, which can be.
So we choose it by validation?
You set it by validation, exactly. So you can use parametric rectified linear unit, and you set this alpha using validation. Yeah, so maybe it's a hyperparameter, and maybe 0.01 is not perfect, so you just set it using validation. Okay, so summary of activation function. This is very important. If you didn't get, again, most of the stuff there, or you got lost in the detail, this is important for training neural networks. For hidden layers, use ReLU. This is the state of the art right now. So use the ReLU as an activation function, and that's a parameter you set while setting up your the library. Yeah. So while setting up a neural network model, you have to specify what is the activation function for every neuron that you have. Use ReLU for hidden layers. Try out other activation functions such as tanh or leaky ReLU. You can do that, but don't use sigmoid. Sigmoid has a lot of issues. It will make your training very slow. The weights will not be updated in a lot of the cases. So avoid using sigmoids for hidden layers. Okay, start with ReLU. If things are not perfect, you can try tanh or leaky ReLU. Yeah, but most of the time the ReLU would work just fine based on a lot of experiments and a lot of experience from projects in general. For the output layer, use either sigmoid or cross entropy error if you're doing binary classification. If you're doing binary classification, you will have one neuron at the output layer, and you use sigmoid for that. Why? Because I want to output, right, a probability of the class being positive, so I use sigmoid. If I'm doing regression, I will use a linear function, so the output layer becomes a linear function, and I use mean squared error for regression. And if I'm doing multi-class classification, I use something called softmax and cross-entropy error for multi-class classification, which is the topic we're going to talk about next on Thursday. So again, right, how do I set up a neural network? You have to specify the activation functions. You have to specify, of course, the number of neurons, the number of hidden layers. We'll talk about this in more details later, but you would have to specify these things, yeah? And you have to specify the type of activation. Use the ReLU for hidden layers, and try other activation functions if you want, and you can set it, you can decide based on validation. And then for the output layer, depending on what type of problem you have. If you're doing classification, binary classification, you use sigmoid, and you have one single neuron in the output layer, and you use cross entropy. You have to specify the type of error so that the neural network gets trained. If you're using regression, then use a linear function. So basically output the signal as is and use mean squared error. And if you're using multi-class classification, you use what is called softmax and cross entropy. We're not going to do one versus one or one versus all in neural networks. Any idea why? Final question for you.
I think that's because you're internally doing it.
First of all, I can do it using neural networks, so right away, but it's more about training time, efficiency. Yes,
not efficient.
Yeah, it's basically, or Hamza, sorry. So it's basically, neural networks are very hard to train. They take a lot of time. Yeah, so it's not like all the other models which can run in a few hours and you're done. You usually take, a lot of hours and if not days. So you can't afford to, train N choose 2 or K choose 2 neural networks, different neural networks to do a multi-class classification. Yeah, so that's why I use something that a different thing. One neural network that can do multi-class classification, and we'll see how to do this in the next lecture. Okay, I'll stop here.
Sir.
Yes.
So is this for any neural network, or and are there any different activation functions?
So these are the most common activation functions for neural networks. So these are the only ones that I'm aware of. They're popular ones, yeah. And yes, it's for any neural network. We'll look at later on what is called convolutional neural networks and recurrent neural networks. Again, they use the same activation functions, but they have different architectures. So we'll see how they work in like a couple of weeks.
Okay, thank you.
You're welcome. Other questions? Okay, so we'll try to finish this on Thursday, and then on Tuesday you have the exam, and then I guess, right, on Thursday we'll start convolutional neural network, and then you would have the assignment on neural networks on Sunday. You would have it, basically it will be using Keras, so using TensorFlow. So you'll start using a different library, which is very popular for neural networks. Okay. Questions?
Sir, I read that sklearn is not good for neural networks. The implementation is not good.
For Keras is not. Which one is not good?
No, sklearn.
Yeah, for neural networks, it's not commonly used for neural networks. Yeah, so that's why we're moving to TensorFlow. It's very slow for in sklearn, and a lot of things are not supported there. So then there's no enough implementation there. So that's why we're gonna move to TensorFlow.
Okay.
Rasha, softmax, we're gonna talk about it in the next lecture. So we haven't discussed what this is. It's used for multi-class classification using neural network. Okay.
Professor, so the exam will be on Tuesday. It's open book, right? and it's
I
model
think it's
based.
not open book. It's multiple choice questions, so it shouldn't be open book. Yeah. So, but I can't. I mean, I will not be able to enforce this. So it's up to your ethics, but it's not open book.
How many questions?
32.
32.
32, yes. 32 in an hour. That's more. That's now plenty of time.
Oh, okay. So it's not an hour and 15 minutes like last time.
No, it's an hour. Exactly an hour.
All right. Thank you, sir. يعطيك العافية.
Yalla. Any other questions? Okay. We'll talk.
انا الكاميرا عندي على اللابتوب منزوعه so كيف بقدر اعمل الاكزام؟
We're not. Most likely, I'm not going to ask you to turn their cameras on. I will not be able to proctor 50 people. So the idea is I'm trusting you, and I hope this doesn't bite me in the neck later on. Okay.
Okay, sir. Thank you.
Thank you, sir. Bye.
If we have technical issues,
So I'm going to be monitoring the exam very closely. If you have technical issues, please let me know by email or something like this, and we'll do it on a case-by-case basis. Yeah. So I cannot write technical issues right now, but if anything happens, I'll be available, and we'll deal with it.
all right.
Okay. Okay, guys. Talk to you on Thursday.
يعطيك العافيه.
Bye bye.
Thank you, Bob.